So, what if market crashes aren't just about economics? What if they're actually physical events? I mean, what if the very same laws that govern things like heat and energy could actually predict the next massive financial meltdown? It sounds kind of out there, I know, but it's a radical new idea, and we're going to break down exactly how it might work.
This is it, right? This is the trillion-dollar question. For the better part of a century, the smartest people in finance have been trying to build a crystal ball for the market. Some way to see the hurricane before it makes landfall. But here's the fundamental flaw with pretty much every model we have today. They're all reactive. They are fantastic at telling you that you're in a crisis, but only after the crash has already started. It's like having a smoke alarm that doesn't go off until the whole house is engulfed in flames. Not super helpful.
And the real world consequence of being late to the party? Well, it's painful and it's expensive. It's a phenomenon called the whipsaw effect. Just when the market hits rock bottom, the old models finally scream, sell, forcing you to lock in those brutal, devastating losses. It's a portfolio-destroying cycle, and it's all driven by looking backward instead of forward.
Okay, so what if we've just been looking at this all wrong? There's a new patent out there that suggests a pretty radical shift in thinking. It says, let's stop treating the market like a messy collection of irrational human decisions and start treating it like a physical system, one that has to obey the unbreakable laws of physics and geometry.
This whole idea is wrapped up in something called a thermodynamic phase inference engine, or TPE for short. And really, it's an early warning system for the market, built on three powerful and honestly pretty mind-bending concepts, borrowed straight from physics and advanced math. Let's dive into that first pillar. So pillar number one reimagines the entire world of investing through the lens of thermodynamics. Yeah, the same physics that explains how your engine works or how ice melts. Okay, stick with me here, it's actually pretty intuitive. In this model, energy is just your potential profit, your risk-adjusted return. Entropy is diversification, how spread out your investments are. Think of it as a healthy kind of chaos. And temperature? That's simply market volatility. The whole game is to find the perfect balance between making money and staying safe, and that balance is dictated entirely by how hot or cold the market is at any given moment. Now, this is where it gets really cool. Think of it like market weather. When the market is calm, a low temperature, the system naturally favors concentrating its bets on those high-return assets. It's time to make hay while the sun is shining. But when a storm rolls in, high temperature, high volatility, the system's priority completely flips. It's no longer about chasing returns. It's about diversification, about seeking safety. It's the classic trade-off between exploring for big wins and exploiting what you know is safe, all driven by the market's temperature. All right, so the system can take the market's temperature right now. That's a great start, but it's not enough to predict what's coming next. For that, it needs a memory. And that's where Pillar 2 comes in, using the principles of geometry to build one. Now, this isn't about just remembering old stock prices. This is something called holonomic memory. It's a really clever way to measure if the fundamental rules of the market are starting to change. It uses the mathematics of curved spaces to detect if the relationships between different assets, like stocks and bonds, are beginning to stretch in warp. And here's the perfect analogy for it. Imagine you're standing on the surface of the Earth, and you try to drive at a perfect square, 1 mile north, 1 mile east, 1 mile south, and 1 mile west. Guess what? You won't end up back where you started. There will be a small gap. That gap is called holonomy, and it's mathematical proof that the world is curved. In the financial world, when that holonomy gap starts to grow, it's a huge red flag. It means the market's underlying geometry is changing. The old rules no longer apply. A big shift is coming. So we've got a thermometer to read the present and a geometric memory to understand the past. But how does the system actually use this information without triggering that awful whipsaw effect we talked about? Well, that's where the third and final pillar comes in. Now we get into some really advanced math called sheaf theory, but don't let the name scare you. All you really need to know is that it acts like a master architect, designing a system that can perfectly glue together the different market states, a bull market, a bear market, a full-blown crisis, so that the journey between them is perfectly smooth. And that's the whole point. This gluing process gets rid of the sudden, jarring jumps that plague the old models. So instead of slamming on the brakes and getting whipsawed, the portfolio makes a smooth, controlled transition from one market environment to the next. It's the key innovation that prevents those painful, reactive losses.
All right, this brings us to the main event. We have the thermodynamics, we have the geometric memory, and we have this slick architecture for smooth transitions. So how in the world does all this come together to create a real, actual, predictive early warning signal?
It's basically a three-step process. First, the engine constantly models the market's thermodynamic state, its temperature. Second, it uses that geometric memory to track its path and see if the rules are changing. And third, it keeps its eye out for one very specific mathematical signature, a fingerprint that screams that instability is right around the corner. And this is it. This is the secret sauce. Now, don't worry about the formula itself. What it's doing is tracking how the market's total potential, its free energy, is changing as the temperature or volatility goes up and down. When this number suddenly spikes, that's the alarm bell. In physics, a spike like this means water's about to freeze or boil. In finance, it's the tremor before the earthquake. It's the signal that the market itself is on the verge of a phase transition, a crash. Okay, it's a beautiful theory. The formula looks clever. But come on, does any of this actually work in the real world? That's the question, right? Well, the patent laid out some detailed simulations to find out. First up, damage control. During a simulated crisis, the traditional reactive models just got hammered, but the portfolio guided by this new physics-based engine, it cut the maximum losses by an incredible 32.8%. And why? Because it saw the punch coming and it had time to get out of the way. And this timeline shows you exactly how it did it. This is so important. The old models, they only sounded the alarm 5 full days after the crash had already started. The TPIE signal, that physics-based warning sign, it showed up 5 days before the event. That's a 10-day difference. That's the gap between reacting to a disaster and actually predicting one. Now, you'd think that running all this complex physics and geometry would take a massive supercomputer, right? But here's the kicker. The patent actually claims a 115-fold improvement in computational speed. That means this entire system can run in real time on standard, off-the-shelf hardware. It's actually feasible. So let's just quickly recap the big takeaways here. First, this whole system is about predicting, not reacting. Second, it ditches a lot of traditional economic theory for the fundamental laws of physics and geometry. Third, its architecture is built specifically to smooth out transitions and avoid those costly whipsaw losses. And finally, the simulations seem to back it all up.
And all of this leaves us with one last really fascinating question to chew on. For as long as we can remember, market crashes have felt like these random, unpredictable acts of God. But if a machine can genuinely see one coming before it happens, how does that change the game itself? What happens next?